My name is Andreas, and I will present the paper Learning Fast and Robust Target Models for Video Object Segmentation. The goal of video object segmentation is to separate a moving target from its background. The challenge is to condition a model on the target. This can be difficult if the target drastically changes appearance over time. The first methods, based on deep networks, created target models by tuning pre-trained CNNs on its appearance in the first frame. Unfortunately, this takes a long time and it overfits easily. Others have maintained target models with the aid of auxiliary blocks, such as optical flow, object detectors, and trackers, which increases the complexity. The current state-of-the-art achieves good results with generative modeling, matching image features to a target memory. However, the approach requires a large amount of training data, and the frame rate is still too low for real-time applications. We propose a new approach to address these issues. At its core is a robust but lightweight module dedicated to quickly learn and model the target appearance. In the plot to the right, we see our results on Davis 2016 speed versus Davis 2017 scores. It achieves competitive results with frame rates far beyond the state-of-the-art. When training data is limited, it can even outperform it. Our architecture contains a feature extractor, the target model, and a segmentation network. Together, they form a unit structure. We want the model to be fast and to predict the target well. It should also quickly adapt to changes. It turns out that this can be achieved with the linear classifier, realized as the weights of two convolutional filters. The first filter projects the backbone features to lower dimensionality, and after initial training, it is kept unchanged. The second filter classifies regions as foreground and background and is updated throughout the sequence. This setup affords both stability and adaptivity over time. We trained the target model discriminatively with ResNet backbone features extracted from the first video frame, and the associated ground truth mask, minimizing an L2 loss. We use a Gauss-Newton conjugate gradient optimizer, converging in fewer steps than gradient descent. This lets us train the model in real time, making it robust to target appearance changes. These animations show how the target model scores evolved during the optimization on the first frame. Notice how the scores become increasingly distinct as the optimizations converge. Here are some examples. The input images are shown to the left and the predicted score maps to the right. Comparing to the ground truth in the middle, we can see that despite its simplicity, the target model has produced quite accurate score maps. However, they are of much lower resolution than the original video frames, and finer details have been lost. To rectify this and generate high-resolution masks, we implement a segmentation network. This network has a unit structure with 4 segmentation blocks. In each block, we merge the segmentation scores with deep features from the backbone, starting at the deepest and lowest resolution level, progressively moving to higher resolutions in later blocks. After an upsampling step, we recover the final segmentation mask. Our entire VOS algorithm is summarized as follows. First, we initialize a memory with the first frame features and the ground truth mask. The target model is then optimized with the memory. We then extract features from the next incoming frame and apply the target model to generate a coarse segmentation score map. This is then refined to the final mask in the segmentation network. We finally store the features in mask, and the target model is updated again, adapting it to appearance changes. We train our segmentation network on annotated video sequences from the YouTube VOS and Davis datasets. Each sample in the training set consists of a reference frame and 2 randomly selected validation frames from the same sequence. In each sample, we optimize the target model on the reference frame and train the segmentation network parameters on the validation frames. We evaluate on the YouTube VOS validation set. When no additional training data is used, our approach outperforms the state-of-the-art. It is also significantly faster than previous methods, reaching a frame rate of 21.9 FPS. With a smaller backbone and fewer target model updates, we reach 41.3 FPS, while remaining competitive to recent methods. And finally, some example videos. You see the input to the left, the score maps in the middle, and overlaid masks to the right. Note that we deal with multiple objects by training and maintaining parallel target models, working on joint backbone features but with different masks. The final high-resolution output masks are combined through softmax aggregation before being stored in their individual memories. Code is available on GitHub. Thank you for watching.